Welcome everyone to our Digital Electronics 2 course. Uh, Today's discussion topic is about oscillators, and this is part 2. We have already finished the part 1 in last week. First look at the content. So first topic is about tuned oscillator circuit, then Colpate's oscillator, Hartley oscillator, crystal oscillator. That's mean different types of oscillator, and finally the starting of power amplifiers. We'll have an overview of amplifiers, and the remaining part will be discussed on the next week. Tuned oscillator circuit. So we already know that what is oscillator, and here we'll discuss about tuned oscillator types of circuit. You can see one figure here. The amplifier is here, and some reactance element. For example, it is denoted as x1, x2 and x3. So they are connected in the output and also in the input, and also in the feedback circuit path or in the biasing circuit path. So instead of x1, x2 and x3, we can put the capacitor, resistor, inductor, or capacitor, inductor both. So depending on the various types of reactance element, it can be possible to tune the input or output the reactance, and in this way the output can be easily vary. The types of these types of oscillators are Colpate's oscillator, another one is Hartley oscillator, and another one is tuned input and tuned output. So when this x1, x2 and x3, you see that the table here, for Colpate's oscillator, this x1 must be C, that's when capacitor, x2 must be capacitor, and x3, this one, it is inductor. So two capacitor, x1, x2, and if x3 is an inductor, then this types of oscillator is called Colpate's oscillator. The next one is Hartley oscillator. So if we use inductor for x1, inductor for x2, and capacitor for x3, that's when two inductor, one capacitor, instead of this x1, x2 and x3. So that will be work as Hartley oscillator, or it is named as Hartley oscillator. And the last one is tuned input, tuned output. So for that, x1 and x2 we need to change with some reactance element, and that is LC. That's when inductor and capacitor both. So for x1 and x2, that is both LC and LC, and x3 is nothing. That means there will be no connections on x3. So that will call tuned input, tuned output. So we'll discuss these types of oscillator in next slides. Colpate's oscillator, and the first part is FET, Fate Colpate's oscillator. That's when this circuit is the combination of Fate amplifier. So previously we saw that here in oscillator we can use the amplifier, but it is also possible to combine the Colpate's oscillator with Fate. So in the circuit you can see that C1, C2 and the L. So this is the exactly the same as like the previous one. That's when x1, x2 and the x3. So instead of x1, x2, x3 we have used C1, C2 and L. So two capacitor, one inductor, and rest of the inductor, capacitor or the resistors are used to bias the Fate amplifier. That means it is used for DC bias purpose. So supply voltage is VDD, and in the middle this is the Fate. So instead of the normal op-amp amplifier, we can also use the Fate amplifier for the Colpate's oscillator. So we can build different ways the Colpate oscillator. So one one is a fate or Colpitt's oscillator. For fate Colpitt's oscillator, the oscillator frequency can be found from this equation. So F0 equals to 1 by twice pi root over LC equivalent. So the capacitor and the inductor value we need. So C equivalent, capacitor equivalent, it is equals to C1 C2 divided by C1 plus C2. So the combination of C1 and C2 capacitor. So equivalent C capacitor equivalent we need to know, and that value can be used to find the oscillator frequency, because this for oscillators, all kinds of oscillator, we need to know the oscillator frequency. That is the most important things, that how with which frequency we can generate the signal. IC Colpitt's oscillator. So another types of Colpitt's oscillator is IC Colpitt's. So here in IC Colpitt's, an op-amp is used in the middle. You can see this portion. So operation amplifier is used for these types of oscillators, and you see that the same connections like the X1, X2 and X3, one capacitor C1, another C2 and another inductor L. So this three is for reactance element, and the rest of the resistor, they are for basic amplifications. That's mean for op-amp we need to, if we want to run the op-amp, we need to give some feedback path. So that is the RF, and also the input resistance RI. So that is for basic amplification, and rest of the feedback network is LC, inductor and capacitor combination of that. And here also the equation is same. That's mean oscillator frequency is same like the previous one, and that is F0 equals to 1 by twice pi root over LC equivalent. So C equivalent is also as like the previous one. So we need to find that using the C1 and C2. A Hartley oscillator. So now another types of oscillator, and here we will first look at the Fate Hartley oscillator, one types of Hartley oscillator. So what is Hartley oscillator? Already we know that if the basic resonant elements are X1 and X2 if inductors, and X3 is a capacitor, then the circuit is called a Hartley oscillator. So for Hartley oscillator, here the circuit is shown the Fate Hartley oscillator types. So Fate means we are using one Fate circuit in the middle, this one, not a op-amp, Fate. So the basic resonant X1, X2, you see that the inductors L1 and L2, and for X3 that is capacitor 1, and the rest of the elements, that's been the capacitor, resistor, another CC, capacitors, inductors, they are used for biasing purpose like the previous one. And plus VDD, this is the supply voltage for the Fate circuit. Fate Hartley oscillator, if the inductors have a mutual coupling value, and that is M, so we need to take it account to find the frequency. So the frequency of oscillation will be F0 equals to 1 by twice pi root over L equivalent into C. So this is the frequency of oscillation for Fate Hartley type oscillator, and here the L equivalent is L1 plus L2 plus 2M. So this M is, you know, that I say that this is the mutual coupling value between L1 and L2 inductors. Transistor Hartley oscillator. So in this type of Hartley oscillator, transistor is used as the main circuit, and here the tank circuit like the L1, L2 and capacitor is used as the basic elements R1, X1, X2 and the X3, and here the rest of the things, rest of the elements are used for biasing purpose. Here the frequency, it is f0 equals to twice 1 by twice pi root over L equivalent into C, the capacitor. So you can find that frequency of oscillation of this given circuit. Crystal oscillator. So other types of oscillator, an op-amp can be used in a crystal oscillator. In the crystal is connected in the series resonant path. That's when one crystal is connected with the op-amp connections and operates at the crystal resonant frequency. So this circuit has a high gain and the output is like the square wave signal, and you can see that here two Zener diode is used. That's been a couple of Zener diodes. One, this one another one is here. So two is in opposite directions, and the Zener diode operates at its own voltage, and that is Vz. So when we will get the output from this op-amp, and that will come through the Zener diode, then the final output will be square wave with the amplitude, output amplitude at exactly the Zener voltage, and that is Vz. So whatever the Zener voltage is, it may be 0.7, maybe 0.9. So output voltage will be also at Vz. So like the Zener voltage. Power amplifier. So till now we have already saw that different types of amplifiers, but they are very in small scale. That's mean very small signal can be generated from those types of amplifiers. So that amplifier receives signal from some pickup transistor or some other sources, and then provides a larger version. That's when amplify the output signal to other devices or any other amplifier stage. So they are generally the signals is very small and needs to be amplified sufficiently to operate the output device. So in a small signal amplifiers, the factors are mainly the linearity of the amplification and also the magnitude of the gain. So for signal voltage and current are small on that types of amplifier. But and for that reason, the power handling capacity is very little concern, and power efficiency are not so high. For voltage amplifier also, they amplify the voltage primarily. They are not concerned about the power. For the large signal or for power amplifiers, it is different. Here the main concern is about the power, because it needs a sufficient power to into the output signal to drive any speaker or other any power device for few watts to 10 of watts. That's when it needs a larger amplifications to provide sufficient output power to the devices in the output sections. So the main features of a large signal amplifier are the circuit's power efficiency and the maximum amount of power so that the circuit is capable of handling, and also the matching impedance also. Amplifiers class. So this is a one types of method to categorize the amplifiers. Then and that is by class. That's when amplifier can be categorized as in different ways, but one way is by class. And what is this class? This class actually represent how the amount of the output signal varies over one cycle of operation for a fixed input signal. So how this output signal is varying, that is depending on that the classes are categorized. So first one we'll discuss about class A. There are several types of class like class A, class B, class AB, class C in this one. So the first one is class A. So you can see that the graph in figure A, these types of amplifiers, the output signal varies for a full 360-degree for the input signal. That's been from half cycle is here for upper level voltage, and Next half cycle is for lower level voltage, so total full 360 degrees. So this requires the Q point to be biased at a level so that the half cycle swing of the output may vary up, and also the rest of the half is down without going to a high enough voltage, and that may be limited by the supply voltage. And the zero level voltage you see here, and the DC bias level is starting from in the middle point, class A DC bias level, and the supply is so much high level, so it may not touch the total supply voltage, but maybe the lower than that. But the full 360 degree output swing must happen in these types of uh, amplifier. Then the next class is class B amplifier. So in this type of circuit, it provides an output signal varying over only the one half the input signal cycle, and that is for 180 degree of signal. So the output showing only 180 degree signal, and you see that the class DC bias level is 0 voltage, and from that only half portion is achieved. So rest of the half cycle is not there. So that is not the things that we want. So for that we need the full half cycle, not the only half cycle, we need full cycle. So to reproduction of the full cycle, we need to provide another class B, that's been two class B. One will provide the positive half cycle, another will provide the negative half cycle. So in this way, with the connections of with the combination of two B class B operations, we will get the 360 degree of operation, and that is that types of connection is referred to as a push-pull operation. So in this class B operation, it gives a very distorted output signal, because you see that the reproduction of the input takes place only for 180 degree output. Another amplifier class is class AB. For this type of amplifier, it is used two types biasing condition. For that, for zero base current level of class B and above one half the supply voltage level of class A, both condition is made for class AB. So class AB operation requires a push-pull connections to achieve the full output cycle, and DC bias level is usually closer to the zero base current level for better power efficiency. So for this class AB operation, the output signal swing between the 180 degree to 360 degree. So in between that, because of class A and because of B, combination of AB, so not the same as A or not the same as only B, it is a combination of A and B. Another amplifier class C. For class C, the output is biased for operation at less than 180 degree. So it is very small amount of output it gets, and will operate only with a tuned circuit. So the combination with the tuned circuit, which provides a full cycle of operation. So these types of amplifier is used in radio or communications purpose. Another one is class D. This operating class is a form of amplifier operation using pulse signal. So only for short interval of times, and the rest of the times it remains off for longer interval. So using digital techniques, that's when using the pulse signal, it is possible to obtain a signal that varies over the full cycle, and to recreate the output from many pieces of input signal. So the major advantage of this is that the amplifier is in on state only for short intervals, and it represent the overall efficiency is very high. Amplifier efficiency. So we know that the efficiency of an amplifier, it is defined as the ratio between the power output and the power input. That's when efficiency is equals to output power divided by input power, and this value, that's when the efficiency improves from going from class A to class D. So it is efficiencies are very less in class A but higher in class D. We can see that in class A amplifier, the with a DC bias at one half the supply voltage level, it uses a good amount of power to maintain the bias. At that reason, the efficiency is very poor. For class B operation, the maximum efficiency reaches almost 78.5%, and for class D operation, it is possible to reach over 90% of the efficiency of total power. Since for AB it is falls between A and B, so the efficiency varies between 25% or 50% and in between 78.5%. So here is the table that summarizes the operation of the various amplifier classes. You can see that for A, B, B, C and D, different types of class, the operating cycle, that's mean how much it is operating, full cycle or half cycle, and the power efficiency. So for A class, the operating cycle is 360° and the efficiency varies from 25 to 50%. And for AB, it is from 180° to 360°, and efficiency is between 25% or 80% and 78.5 because it is combination of A and B. So for B, it is operating cycle is 180° and the efficiency is 78.5. And for C, it is less than 180° operations, and for D, it is a pulse operations, not the degree. So the efficiency is very high, that is typically over 90%. And C is usually not used for delivering large amounts of power, so efficiency is not given here. In class B operation, a push-pull connection is also can be possible to maintain, and for that reason we can use a transformer coupling or using complementary operation with NPN and PNP transistors. So it is also possible to couple the NPN and PNP transistors to provide operation on opposite polarity cycles. And though the transformer can provide opposite cycle signals, but transformer itself is a quite large in applications, so transformer less circuit is complementary transistors, and that provides the same operation in a much smaller package. Self-directed learning of this week. The question is compare between class A and class B amplifier. So we have already learned different types of amplifier. So you need to compare between this class A and class B amplifier and write this question's answer into the forum. So that's all for this week. In this week we have forum and the quiz. So please participate on that. And please remember that in next week, that's been in the 12th week, I will have the term paper. I will upload it on next week by Sunday, so you can answer it from Monday hopefully, and you will get approximately 7 to 10 days depending on the final decision that how long it will be open to answer the term paper questions. You need to submit the term paper answer script into the forum that will be uploaded on the under week 12. So you will have different questions, you need to answer it, and please submit the term paper or the assignment in handwritten format, and also definitely in PDF format, not any Word file or in JPG format. Okay, so that's all for today. Thank you.